Cells and batteries are essential components in modern technology, providing portable and reliable sources of electricity for a wide range of devices. The fundamental principle behind the operation of cells and batteries lies in chemical reactions that produce electricity. Understanding how these chemical reactions work, why the voltage of a cell can vary, and why non-rechargeable batteries eventually lose their ability to generate electricity provides insight into their design and function. In a typical electrochemical cell, electricity is produced through redox reactions, where one substance undergoes oxidation, loses electrons, and another undergoes reduction, gains electrons. These reactions occur at the two electrodes of the cell, the anode, where oxidation happens, and the cathode, where reduction occurs. The anode releases electrons, which then flow through an external circuit to the cathode. This flow of electrons through the circuit is what we recognize as electricity, and it can be harnessed to power devices. The ability of a cell to produce electricity is fundamentally tied to the chemical reactions taking place within it. The choice of materials for the electrodes and the electrolyte, which facilitates the movement of ions between the electrodes, determines the specific redox reactions that will occur. Different combinations of materials have varying tendencies to gain or lose electrons, and this directly influences the voltage, or electric potential difference, that the cell can produce. The voltage of a cell depends on several factors, including the nature of the materials used for the electrodes, the concentration of the electrolyte, and the temperature at which the cell operates. The specific chemical composition of the electrodes is crucial, because different materials have different electron affinities and ionization energies, which determine the magnitude of the potential difference between the anode and cathode. For example, a cell with a zinc anode and a copper cathode will produce a different voltage than a cell with a magnesium anode and a silver cathode due to the differing reactivities of these materials. The concentration of the electrolyte also plays a significant role in determining the cell's voltage. As the concentration of ions in the electrolyte changes, so does the ability of the cell to maintain a steady flow of electrons, which can affect the voltage. Additionally, temperature impacts the rate of the chemical reactions and the mobility of ions within the electrolyte, thus influencing the cell's voltage. Higher temperatures generally increase reaction rates and ion mobility, which can lead to a higher voltage, while lower temperatures can have the opposite effect. In non-rechargeable batteries, often referred to as primary cells, the reactants that fuel the redox reactions are gradually consumed as the battery is used. Unlike rechargeable batteries, where the chemical reactions can be reversed by applying an external electrical current, non-rechargeable batteries are designed for a single use. As the battery discharges, the materials at the electrodes are transformed into new compounds that can no longer participate in the original redox reactions. For example, in a typical alkaline battery, the zinc anode is oxidized to form zinc oxide, and once a significant portion of the zinc has been converted, the battery can no longer produce electricity. The depletion of reactants in non-rechargeable batteries is an irreversible process. As the reactants are used up, the amount of available energy decreases, leading to a drop in voltage until the battery is no longer able to power devices. This is why non-rechargeable batteries eventually die and must be replaced. In summary, cells and batteries generate electricity through chemical reactions in which electrons are transferred between materials in the electrodes. The voltage produced by a cell depends on the specific materials used, the concentration of the electrolyte, and the operating temperature. In non-rechargeable batteries, the reactants are gradually consumed as the battery discharges, leading to a loss of the ability to generate electricity, which eventually renders the battery unusable. Understanding these processes is essential for the effective design and use of batteries in various applications.